Good morning, or good afternoon, or good evening to everybody, and thank you very much for joining today's webinar. My name is Richard Smith, and I'm Global Applications Manager at Taylor Hobson. Today's webinar is called Roller Bearing Measurement and Analysis, and it's an overview of Taylor Hobson's range of new capabilities. This forms part of a series of Bearings Solutions webinars. So let's get started. The start of this is with a brief introduction to roller bearing measurement and why we measure roller bearings. We'll have a look at a new method of measuring roller bearings without the need for complex fixtures. We'll then look at analysis and tolerancing, and another way of measuring roller bearings by detecting the beginning and end of the measurements, so we don't need to enter the traverse length, and also at a vacuum chuck, which is available now on our Talyrond500hs systems for both roller bearings and ball bearings and other such components. Finally, we'll have a look at multi-part measurements. So let's make a start with an introduction to roller bearing measurement. On the left here, we can see figure A, B and C. In figure A, we have the roller bearing here and a representation of the grinding tool. And in this case, in figure A, we're showing the correct tool alignment to the roller bearing, and this produces a component, an ideal component that will be well in tolerance. In figure B, we can see that the tool is offset from the roller bearing here, and what happens is that this moves the center point of the bearing left or right of the bearing axis, and we can see the offset there. And in figure C, we can see that the grinding tool is angled to the axis of the bearing, and this would produce a parallelism error between the sides of the bearings, and we'll be looking at that as we go through just now. So let's move on to have a look at the new method of measuring drops and dimensions. Using this new method, we're trying to find the X offset of the crown from the end faces and compare this to the DXF or the design. And the position of the crown from the end faces is crucial, as we've just seen, for the performance of the bearing. And on the right in the picture, we can see the bearing, we can see the end faces, and the center line here is the nominal position of the roller based on those end faces. But the actual measurement across the roller profile here has a different crown in this case, and that is really the X offset error that we're interested in. But to be able to determine this, we need to know where these end faces are relative to this profile. So conventional techniques require references, and what we have to do is put a ball or a cylinder of a known diameter at each end and measure that as well as the bearing. So these fixtures are used to identify the end faces so that we can find the X offset of the crown. But this can add complexity to the setup, and it can increase cycle times. The good news is that for many smaller bearings, a different approach can be used, taking advantage of the capabilities of the PGI Novus and its dual bias gauge. And that's what we're just going to have a look at now in this video. So we've got the roller bearing here on the left, and it's mounted in this simple fixture in these jaws here at 45 degrees. And this allows us just to take just two measurements, one over here like this, and one underneath like this. So we measure the roller profile and the right-hand end face, then we measure the left-hand end face and the lower profile. Let's have a look at this now in the video clip. So I'm just going to pause there and show that we've taken a very, very small trace over the top of the bearing. And what we do is we compare this automatically to the design, to the DXF drawing. And from this, we can determine points around the bearing. These 4 points that we can see in the top right here, I'm just pointing them out now. 1, 2, 3, 4, A, B, C, D. And if we continue the video here, we will see that we've generated these points from the drawing A, B, C, and D. And these are now available as reference points to do the two measurements. So the stylus moves automatically exactly to the start point, and you can see it on the top right there. We're measuring the first single trace. We now change bias so that we can measure with the other tip, the other stylus tip, and we're going to measure underneath now. And again, one long trace here. So without any fixtures, we've managed here to measure the full roller bearing. And what we get is the results which allow us to look at the drawing, the DXF comparison, and the tolerance to residual form. And you can see that here. We also can see the X offset of the crown from the end faces. It's a very small value there, but there is a difference between the centers relative to the end faces and the center as defined by the profile itself. We can also look at diameter. Because we've measured with a very highly precise gauge, we can measure the top face and the underneath face and also know the relationship between them. And we've shown the diameter here. We've also shown roughness and waviness as well. So let's move on now to analysis and tolerancing, having a look at analysis and tolerancing. Here again is the same diagram, but what we're looking at is these things. We're looking at the form error. That's the form error of these main surfaces. This could be incidentally on a cylindrical roller bearing or any other type of roller bearing that, as there are many different types. We've just chosen this example here as a cylindrical roller bearing, and we can get the X offset to the end datum. And if that's wrong, then we can adjust the machine axis if we need to. The profile tilt, that's comparing opposite traces, allows us to adjust the grinding wheel angle if we need to. And what I should have mentioned at the beginning there is that the form error allows us and tells us how to check or dress the grinding wheel. Again, looking at these results, these are toleranced results. One difference here though is that instead of having a single tolerance band, you can see this is split into 5 different tolerance bands. And again, we've shown the form error there. On the right hand side, we can see the X offset value given. We can see the diameter, we can see the drops, and we can see the roughness and the waviness. So moving on now to what we call this 2D X auto capability. This is a new capability which allows us to define the start and end positions of the trace automatically. We don't need to type in the traverse length to do the measurement. So any size bearing we can put on there, and we can base the detection of the edges, the beginning and end of the traces based on a height difference, a gradient difference, or an absolute angle. And this really does simplify the measurement process. It also means that it simplifies the programming as well, and less setup as well. So let's have a look at that now. And my colleague here has just contacted onto the center of the roller bearing, and the left edge is auto detected. The stylus moves in reverse, just finding that edge there. The measurement starts. And it stops when the right hand edge is auto detected. So now we move to measure inside this particular bearing, and we're measuring the internal surface in exactly the same way. We're moving in reverse there to detect that edge and onto the far edge to where the measurement will stop. So whatever the size of that bearing, it will do that automatically. Now we've switched the gauge into reverse bias. This gauge and system, the PGI Novus from Taylor Hobson, knows the precise distance between the two stylus tips here. So that allows us to measure dimensions on this bearing, and we'll see that in a minute. There's just one more trace to go underneath here, and when that's completed, we will have measured 4 traces, automatically detecting the edges. So this is the lower external surface that we are now measuring. And now once that's finished and the measurement stopped there, all the 4 profiles are analysed together, and we can see the dimensions, wall thickness, roughness and waviness here. We can also get the profile drops from the crown. And again, we can see the tolerances using 5 different regions as well. Let's take a look now at the vacuum chuck. The vacuum chuck is a recent addition to the Talyrond500hs range, and it is an option, and it's ideal for small roller bearings, which can be quite difficult to hold in place. Using the vacuum chuck, we've got greater measurement access available, and there is no need for direct clamping or complex fixtures. The vacuum chuck has no effect on the roundness, doesn't create noise, and isn't susceptible to any other influence on the measurement process. It can be controlled by a simple on-off push button or through the software interface, and it can communicate with external sources such as a robot for automatic loading. So on the right there we can see the roller bearing in place on the vacuum chuck, and there it is with a close-up in place, held by the vacuum. And let's have a look at the vacuum holder now. The vacuum holder is available not just for roller bearings, but also for ball bearings and for any other parts for which we can make special fixtures. Ideal for particularly small parts. The holder is diamond turned, and we're now switching on the vacuum, and the ball is being held in place in this cup, precision cup, on the Talyrond system there. We're now taking a measurement, and we can look at the roundness there. In that case, the roundness is 25 nanometers. We've now finished that measurement, and we remove the ball bearing, and we can also we can now remove the holder as well. There's a range of holders available for ball bearings from 0.5 millimeter up to about 30 millimeters. And now we're putting another one in place. Very easy to put in place. Just put it in place, put the ball to be measured on. This is a different size ball, and easy to do that. And finally, we're going to show you a very small ball bearing held in here. So where it really is important to be able to hold these properly, and this vacuum chuck is ideal for this. So now the ball is presented there to the holder, the vacuum is on, and the stylus tip is slightly large there. We would probably use a diamond stylus for that, and the measurement takes place. Once the measurement's taken place, we can have a look at the harmonics on that ball, or we can look at the roundness results as well. And here are the roundness results, the roundness there of about 36 nanometers. and the harmonics results as well. Once the measurement's finished, we can switch off the vacuum, easily remove the ball, remove the ball holder itself, and finally remove the vacuum chuck as well. And once that's removed, the system is available for standard normal measurements. So we've had a look at the vacuum chuck. Finally, we're going to have a look at multi-part measurements. So the Talyrond500hs, as well as having a vacuum chuck capability, is also able to take a rotary stage or carousel. And on this, we're able to put multiple roller bearings. So the user simply loads the components onto the carousel fixture. And in this example, there are 20 parts. And what happens is the carousel rotates to bring the required part, the selected part, over the instrument axis. And then that is aligned to the instrument axis and centered and leveled to the instrument axis. And then the component can be measured for roundness, surface finish, contour, and so on. And on completion, the carousel moves to the next angular position and the process starts again. So we'll have a look now at that, just a short video of that. So the carousel can be put on or taken off as required. It's plugged in. There's 20 parts there that can easily be loaded into this fixture. This fixture was actually designed for roller bearings. These are test samples, but the original fixture here was designed for roller bearings. Centering and leveling is taking place, then it's measured, the stylus moves clear, and then the carousel can move to the next component that needs to be measured. And the whole process can be automatic, so you can leave this measuring and go away and come back. So we're able to measure roundness, surface finish, cylindricity, flatness, and so on these parts, or any parts. Once the measurements have completed, we can remove the carousel from the system. It's very easy to remove. And we can see here my colleague taking away the carousel, and now that's available as a standard Talyrond for measuring other parts. Once the measurements have been done, this is a study we did on 20 roller bearings, and we measured those roller bearings 20 times. So we've got 20 parts across the top there. We're measuring in nanometers, and down the left-hand side, we're measuring runs 1 to 20. And when we did that, we found that this particular R&R study, we got a standard deviation of less than 10 nanometers and an average spread of results across the whole lot of less than, average spread of 20.6 nanometers. Really good testament there to the sort of results that we can get. So now we're looking at the surface instrument, the Form Talisurf PGI Novus in this case, and running Metrology 4.0 software. And on the right, we've got a production interface set up with, we've just shown 5 here, 1, 2, 3, 4, 5 bearings, but actually we could measure many, many more roller bearings, and they can either be measured individually or selected bearings can be measured. They can be different sizes. And the production interface allows us to do that. Just by simply pressing the play button here, we can start and complete the whole process. Once the results measurements have been done, we have a set of results here. In this case, we can see 2, 2, 3, site 1, site 3 and site 5 have passed. Site 2 and site 4 have not met specification, but it's clearly indicated here, the level of errors are indicated, and the tolerance results are all tabulated with a clear pass-fail indication. The results can be saved as a report and as a PDF. That's the actual results, the graphs and everything is all saved in one complete report. So in summary, for what we've looked at today, we've looked at rapid roller bearing measurement using a new method by tilting the bearing. We've looked at some roller bearing analysis and different ways of tolerancing the results. And we've looked at a simplified method of roller bearing measurement where we detect the beginning and end of the measurements that we're taking. We've also had a look at the vacuum chuck for use with roller bearings and other elements such as ball bearings. And then we've had a look at multi-part measurements both on the Talyrond system using the carousel and also on the PGI Novus using the production interface. So I think at that point we'll stop for any questions. So we have two questions in. The first question that we've got is how do you maintain accuracy using the carousel or the rotary stage on the Talyrond holding so many parts? That's a really great question. The carousel itself has a counterbalance weight in it that keeps the weight, keeps the load on the spindle axis exactly symmetric about the spindle axis. And so there's no degradation, no loss of accuracy in the results that we get. I think you saw on the table of results there that we were achieving incredible accuracy on roller bearing measurement. And the second question here is, can 2DX Auto be used for other parts than roller elements, as you showed? Yes, it can. That's the simple answer. We've shown there a roller bearing where we used the beginning edge and the end edge where the stylus falls off, just starts to fall off at the start of the measurement and stops at the end of the measurement. That's a beginning and end of trace. We can equally drive from a known position to an end, or we can just start and then stop in the middle of a trace rather than having to wait until it hits the end. We can also measure parts other than rolling elements, for example, parts that have a slightly positive slope. The roller elements have a negative slope on them, but ones that have a positive slope. So anything really where we can define an edge, and we can define that edge using an absolute reference or with reference to an absolute position as an angle, an absolute angle, and we can do it as a drop as well, or we can use it as a change in angle as well. So several different ways of detecting those edges, and really a hugely time-saving device. Okay, that's brought me to the end of the questions. Just to say a couple of words here about the support material that we have. We have some application notes, A151 and A156. The one on the left there is for high precision multi-part measurement, and it deals with what we saw, which was the carousel, the rotary stage measuring multiple parts. And again, it shows that study that we looked at in that application note. On the right hand side, there is one saying rapid roller bearing measurements, and that's that new method of holding the bearing at 45 degrees where you don't need so many fixtures to identify the end faces. And the same story that we've just been through now is told in that. And finally, just to say, there is a general bearings applications brochure also available from our website as well. So that brings me to the end of this webinar. There will be future webinars coming out in the application series. And finally, just to say thank you to everybody for attending. Thank you very much.